Okay, Chapter 9, Static Equilibrium and Elasticity. We're going to talk about two major concepts in this chapter. Not surprisingly, they're going to be first, equilibrium, some conditions that we need to have for equilibrium, which we can then go ahead and use to solve statics problems, which will be of particular interest to people that are going into engineering. We will apply solving statics problems to muscles and joints and talk briefly about stability and balance. The other main concept here is elasticity, stress and strain. What happens when you put too much stress or strain on an object? Obviously, we're going to get fractures. And lastly, we'll talk about how all of this goes into spanning a space, building a bridge, and even architecture a little bit. So, conditions for equilibrium, I'm going to give you the first one right here. If we have an object with forces acting on it, but it is not moving, then condition number one, that object is in equilibrium. Here we have a book. It has two forces acting on it. These forces balance each other out, so this book is in equilibrium. I do need to correct the book very briefly here by saying that this is a special type of equilibrium. It's going to be static equilibrium, hence the name of the chapter. There is another type of equilibrium that's going to be called kinetic or dynamic equilibrium, and in that case an object can be moving and all the forces acting on it will balance each other out. So therefore it's not accelerating, but we do have other types of equilibrium. We're only considering static equilibrium for this chapter right here. So let's take a look at a chandelier that has some forces that are acting on it. However, it is not moving. Obviously we would draw the free body diagram for this guy, and we would have the weight of the chandelier going in the downwards direction. This is example 9.2. We'd have some tensional force going upwards from this chord A, as well as some force in chords B, and essentially what we would want to do is we would want all these forces to balance each other out. We want to say the sum of the forces in the x direction must be equal to 0. Similarly, all the forces in the y direction must be equal to 0. In the y direction, we're going to have force A, some component of that in the y direction, which we can figure out knowing the angles, minus the weight. And in the x direction, we're going to have force AX acting in the negative x direction, and force B acting in the positive x direction. And the way that we go about solving this guy is we take this equation right here. We know the weight. We go about and we solve for the force A in the y direction. We can relate that back to the force and the force A in the x direction using trigonometry, and then we have a roundabout way of solving for force A in the x direction, and we can figure out how much force is going to be supplied by the wall on this side over here that we're calling B. So the second condition that we have to worry about for equilibrium is that there be no torque about any axis. If we look at my ruler here and say that it has some length L, I can say, well, this force is equal to this force, therefore in the x direction there is no net force. However, if I stake this guy and put a hole right through the center, drive a nail through there, we can see that I'm going to have a force acting on some lever arm of L over 2, and then I'm going to have another force acting on another lever arm of L over 2. So I'm going to have a net torque on this guy that's going to be, I'll clockwise to be my positive direction just for a change, force L over 2 plus force L over 2, or equal to the force multiplied by the length. And just to say that the choice of axis is going to be arbitrary, if I drilled a hole and I put my nail right here, obviously we'll get no net torque from this guy. However, we still get a torque that is equal to force multiplied by length from this second force over here. So solving statics problems is actually very similar to solving Newton's second law problems. We're going to choose our object, or objects if there's more than one, split them up, and we're going to draw the free body diagram showing all the forces on that, as well as where they act being any distances involved. Choose a coordinate system that makes sense, pick your x-naughts and such so that 0 makes sense, as well as take any forces and break them up into components. And then steps number 3 and 4 deal with this thing called equilibrium, where we want to say that the sum of the forces in the x direction will be equal to 0. You want to say that the sum of the forces in the y direction must be equal to 0. We know that it is in equilibrium. And last but not least, we want to say the sum of the torques must also be equal to 0. So our second criterion for equilibrium. Now we have essentially 3 equations we can solve for up to 3 unknowns. So just the previous slide might not solve every single static problem you ever come across, but that is the best starting point, and it will solve all the problems that you'll encounter in this classroom. One thing that we have to start taking into account here is that the objects are now going to be large objects, and they're going to have some center of gravity, and we'll have to take into account the weight of objects that act about the center of gravity. Here we have the center of gravity of this table, and if I looked at this as a statics problem that said, okay, this table is in equilibrium, solve for this force here, force B, you know kind of intuitively that it's going to be larger than force A because you have this big honking copy machine, or whatever the heck this thing is, sitting closer to leg B than leg A. We want to go about solving this guy, so we want to say, okay, we want all of the forces in the y direction to be equal to 0. We also want all of the torques to be equal to 0. And one thing that we can do is we can choose our pivot point fairly intelligently. If we chose my pivot point right here at point P, then we know that force A is not going to cause any torque because it has 0 lever arm. So we can eliminate one of our variables by a simple yet sophisticated choice of the pivot point. Now we can go ahead and we can write what all the forces in the y direction are and what all of these torques are, just being very careful to know that the axis of action for the force is going to be here, here, and here, and the lever arms for the center of gravity, the lever arm for the copy machine, and the lever arm for the force B are going to be those 3 distances respectively. So just kind of a note about solving these statics problems. Suppose you had a statics problem where you had to solve for some forces on this table right here, and you went ahead and you said, okay, well I know that this force A is going to be up, this force B is going to be down, and I know that some weight is going to be in the downwards direction right here. And then you go ahead and you solve all this guy out, and it turns out that your force of A is equal to some negative number right here. That doesn't tell you that you did the problem totally, utterly incorrectly. All it tells you is that you chose your force A to be in the wrong direction. So essentially, A is not going to be supporting the table. A is going to be essentially holding the table down as the center of gravity wants to make the table rotate in that direction right there. So you don't necessarily need to worry about getting all the signs of the forces right before you start solving statics problems. So let's take a quick look at solving a sample static problem. One thing to keep in mind is if there's a cable or cord, it can only support forces along its length, and forces perpendicular to that is going to cause it to bend. So here we have a sign that is being supported by a cord, so we're going to have a force only along the direction of that cord, and a hinge and a beam. Notice that the sign has got some weight, the beam has got some weight. What the book has done is it's done the first couple of steps for you, is it's identified all the forces and broken them up into their x and y components. So we're going to have some tensional component in the y direction, some tensional component in the x direction, where we know what that angle is going to be. We can't ever forget that now we have beams that have some mass associated with them. And lastly, when it comes to all the forces of the hinge, we don't really know a whole heck of a lot about that. So the book's taken a stab at which direction they should be in, but as I said on the last slide, if we chose these directions to be wrong, the math will tell us at the end of the day. So what we want to do is we want to say, okay, well, this object is in equilibrium, all the forces in the x direction should be equal to 0, and I'm going to have the force of the hinge in the positive x direction and the force of the tension in the x direction. So I can solve this guy for the force of the hinge, and it comes out to be positive, so I chose my direction to be correct. One word of warning is just be very careful with your directions and remembering which direction you drew the force in, especially if you drew it in the wrong direction, it came out to be negative. Then what we want to do is we want to say what are all the forces in the y direction. Those guys also need to sum up to be 0. So we're going to have the mass of the beam in the downwards direction, we're going to have the mass of the sign in the downwards direction, and we're going to have the force of tension in the y direction, and then the force of the hinge in the positive direction. Now the last equation we want to write is the sum of the torques must be equal to 0. And this is where choosing your pivot point can make your life a little bit easier. You might think, well, I'm going to choose my pivot point here because it's the hinge, and yes, you can certainly do that. However, if I go ahead and I choose my pivot point to be over here, you can choose this to be anywhere, then I don't have to worry about a torque from this guy, and I don't have to worry about a torque from that guy. I only have to worry about torques from here and here. It simply makes my life a little bit easier. So to go ahead and write these torques, I'll start with the force of the hinge that is going in the clockwise direction, so I'm going to call that to be negative. Force of the hinge multiplied by the length of the hinge. And then we also have in the counterclockwise direction, or the positive direction, we're going to have mass times gravity multiplied by the length of the hinge divided by 2. We know what that is, so we can go ahead and we can solve, this is force of the hinge in the y direction only, mind you, so we can go ahead and we can solve for the force of the hinge in the y direction only. Now we know everything that there is to know about this hinge. We know the force in the x, and we know the force in the y, so we can go ahead and we can plug that guy in right there. There should have been a y there. And we can solve this guy for the force of the tension in the y direction. Knowing all the angles, we can solve for the force of tension. We can use the same type of analysis for applications to muscles and joints. For example, here we have someone holding up a ball in their hand, and we have a force of a muscle, we have some weight of their arm, we have some weight of some ball, we can go ahead and say, okay, my elbow is going to be the pivot point, and I can say I know that this is in equilibrium. So all the torques must be equal to 0, as well as all the forces in the y direction must be equal to 0. There are no forces in the x direction here, but we could also write that as well. Define our pivot point and say, okay, well, this muscle is going to act at 5 centimeters, the center of gravity is going to act at 15 centimeters, and then the ball is going to act at 35 centimeters, and go ahead and solve for this force of the muscle. And similarly, we can go ahead and calculate what the force of the joint would be simply by using this guy right here. We can also do the same thing if the arm is at different angles, where we just simply have to go ahead and figure out what the different lever arms are. We can also use these conditions of equilibrium to take a look at why you should lift with your legs and not with your back. Essentially, we can treat a man's spine as being in equilibrium as he lifts something up. We can go ahead and we can look at his vertebrae. We're looking at example 9.9 here for you following along in the book, and we can draw all the forces acting on this guy. We can write that the sum of the forces must be equal to 0 in both the x direction and in the y direction, as well as the sum of the torques must be equal to 0. And it turns out, especially using the sum of the torques, you can see that the force of the muscle is going to be at a very, very, very small lever arm, and so it's going to put a large strain or a large force on his vertebrae and could potentially damage this guy. However, damage this guy's back. However, if he did all of the lifting with his legs, where the muscles are at relatively larger distances away from the joints, then he can lift that with much less danger of straining a muscle or hurting a joint. We can talk about two types of stability. Here we have a simple pendulum, and if we take that pendulum and we just give it a little push to one side, then the net force is going to act towards its original position, and if it swings back and forth for a while, it's going to return to where it initially started. It's going to return to its equilibrium position. This type of equilibrium is called stable equilibrium. Another type of equilibrium is going to be unstable equilibrium. If I take a pencil and I balance it on its end, then we can say, okay, the sum of the forces, sum of torques, all that good stuff, this pencil is in equilibrium. All of these guys add up to be 0. However, now if I take this pencil and I just give it a tiny little shove to the side, and it tends to move away from its equilibrium point, then I say that this object is in an equilibrium that is not stable. So it's unstable equilibrium. Two mighty fine ways to look at if an object is in stable or unstable equilibrium is to consider its center of gravity and say, okay, if I shift this guy, what's going to happen over to the side? Then what's going to happen to its center of gravity? If the center of gravity goes down, we're going to decrease the potential energy. Therefore, this object is in unstable equilibrium. For this guy right here, if I push it off to the side, the center of gravity is going to move up. Therefore, I have increased this object's potential energy. This object is in stable equilibrium. An object that is in stable equilibrium can actually become unstable. For example, here we have the proverbial refrigerator. We're going to push that guy off to the side. you can see that we've increased the potential energy. However, once the center of gravity passes over the pivot point, then the center of gravity starts to go down as you push it more and more off to the side. Therefore, we can take an object that was in stable equilibrium, pass the center of gravity over the pivot point, then it becomes in unstable equilibrium. One last thought on stability and balance. If you're carrying a backpack or if you're carrying a briefcase, what you're doing, whether you know it or not, is you're always adjusting your posture such that you keep your center of mass directly over your feet. If your center of mass was not directly over your feet, then you'd be falling over. So here this fella is leaning over to compensate for the weight of his laptop. Here this lady is leaning forward to compensate for the weight on her backpack. And while this is okay for small loads, if you're carrying a heavy load, a heavy backpack, you're going to be leaning forward quite a bit, and over time the contortion could cause some injuries.